All right, good morning, Etechians. And to Mr. Lake's class, good afternoon. Period 1, Etech, would you like to say hello to Mr. Lake's class? Hello. All right, that's nice. They're a little more awake this time. This is take 2, actually. So, we ended with our video last time of Maxwell's equations that explain electricity and magnetism. And if you would like to know this stuff, go talk to Mr. Lake. So, electromagnetism. Now, I'm going to have a little thing here. Let's say some aliens came to Earth. And the one in the middle here is the commander. And these are his 2 lieutenants. And he says to his lieutenants, go out and meet Earthlings and describe and report back. So this guy over here on the left, he goes out. Well, because they're aliens, okay? They don't know Earth. Okay, this come here. And they find an Earthling. And so the left-hand lieutenant, he starts describing, in his little journal thing, he's describing, this Earthling, okay? And we could call this Earthling we'll call this one Electro, okay? Just give it a name, okay? Now the other alien, he's walking around, he discovers an Earthling as well. So he walks up to this Earthling, and he starts trying to talk to it, and he's explaining. And now we look at that and we laugh because, hey, we know those are both horses. We've seen that, but they're not from Earth, okay? So, they don't realize that this creature is actually the same as this creature. And that's how it was with electricity and magnetism for a long time. It took Mr. Maxwell to put electricity together. Electricity really got studied with Benjamin Franklin. Magnetism, people knew about for centuries, but we didn't realize that they were the same thing. So that's my intro to electromagnetism, that depending upon which side of an animal you walk up to, you're going to get a different view, different characteristics, and it might take you a while to realize, hey, they're the same thing. Hey, I was in there. I didn't mean to. That was a funny pun. Okay, so let's see. What's the next thing here? Okay, electricity. Now on this side here, we got electricity notes here. So electricity is moving electrons. Oh, I should have used a cow, because then I could have said moving electrons. I'll have to fix that one here. Electrons are the outer part of atoms. And the spinning of these electrons can create a force field. In physics, there's this rule. It's called the right-hand thumb rule. Let me zoom out. Zooming out. Maybe do I need to turn my light on? Oh, can you see my hand here? Okay, well, I don't have much light there. Do I need to turn the light on there? Oh, there we go. Anyway, what this means is if we've got a circular coil of wires, my fingers will represent the direction of the coil. If we've got moving electrons through it, those electrons are going to they're going to induce a force field. And your thumb will always point in the direction of that force field. This is called the right-hand thumb rule. You don't really need to write that down. It's just really cool. I don't know why you wouldn't want to write it down. So these spinning electrons, they can create a force field. Now, you might think that's magic. It's not. It's science. So we got a diagram there showing the parts of an atom and the outside part of those electrons. So as those electrons are spinning around, they're going to induce a little force field. Isn't that cool? See, this is why physics is really just an explanation of chemistry, okay? Now, let's draw this down below. Let's draw several atoms on there. Now, atoms don't always get their orbitals aligned. So we'll draw some little spinning tops. Let me see if I can adjust that. That doesn't really make any difference in color. If I zoom in, does that help a little bit? Okay, so we've got these atoms. Now, this is what happens in most metals. The atoms, when they cool, when they're from a solid form, they end up They end up in random arrangement, okay? And you've got, look at here, you've got the magnetic line of force going that way, this way, on this one that way. They're not aligned. Go for it. Thank you. Now let's talk about a magnet now, okay? So now we're on the magnetism side. Now, when an object becomes a magnet, or when it gets in when metals get in the influence of a magnetic field, these can all end up aligning. If you apply a strong magnetic force to these atoms, they're going to line up. Just like the compass needle on a compass will align to true north. Okay, I think I got one here somewhere. Okay, maybe not. I think my science Olympiad just took it. Okay, well, if I had one here handy, I'd show you. Oh, there's where those are. Okay, so all of these in here are now aligned. It's turned this piece of metal into a magnet. So that we're having there force field from magnet to other magnets. This force field can interact with the force field of another magnet. And if you like, you can use the symbols for iron, nickel, and cobalt, Fe, Ni, and Co. The three elements that can naturally be a magnet are iron, nickel, and cobalt. In fact, what's really cool, on the periodic table, oh, you can't see that. Did I turn this light off again? There we go. Here's iron, nickel, and cobalt right there together on the periodic table. There's no coincidence there, okay? And it's the old, oh, I can't remember the old group number. Can you guys, the old group, is it 8B up there, guys? Can you see it closer? I don't have all those old group numbers. So it's cool that naturally those are the three naturally occurring metals. Now, some other elements like neodymium, samarium, and there's some other ones can be used with those to augment the strength. That's where you get those really strong magnets called rare earth magnets. But for the most part, I don't want to get this too close to my computer. Here's a common magnet. This is called an alnico magnet. It's aluminum for lightness, then it has nickel and cobalt in it for strength. A lot of times I think farmers use these. They let their cows swallow them. So if cows, as they're eating, eat like pieces of metal and stuff, this will attract it and it doesn't go through their system and kill them. Alnico. Okay, you don't care about that. Now let's see here. What do we got here? Metals moving through magnetic fields can push electrons in the metal. Okay, so now, if we've got some metal and we've got a magnetic field, we can make these electrons begin to move. We can make an electric current. And I think I got a demo of that. What's the next one here? Oh, back up here. So while you're finishing writing that, got this really high-tech demo set up here for you. Can I move that for a moment? You done with that? I'll put it back. So the point here is metals moving through magnetic fields can push electrons in the metal. This is how our generators work. Okay, here's a voltmeter. Turn it on. Got it hooked up. Here's a coil of wire. Oh, wait a minute, sorry. Is that better? Zoom out. Okay, we want to get, so can you read the numbers on there? Excellent. Okay, so I've got this set to 200 milli amps over here, DC amps. Now, watch this. Here is a really weak, lame bar magnet. They're really not lame. They have a job. They're supposed to be weak. You can see there's the north end of the magnet, south end. Now, when I stick this through here, see how it's creating some milliamps? Not a whole lot. This is a weak magnet, and it's not the best coil. But do you see that we're getting some amperage going through? Turn this over to micro, to milli, yeah, that's going to be millivolts. So if I push this through, okay, look at there. We're inducing a current. So I know what you're thinking. Yeah, magnets are magic. They both start with MAG, and it is really cool. I think if there is any magic in the world, it's either magnets or when you look into the eyes. Okay, you don't care when you do that. So anyway, so when you have a magnetic field, and you're pushing it past some metals, you can make the electrons in those metals, again, the metals, the copper inside of here, begin to move, and we get a current. Okay, back to this. Can you see that now, okay? Okay, out angle there. No, I don't want to do that. So next one right here. Here's a diagram. What I'd like you to do is, if you could, like, kind of draw this one. This is representing what they call the domains in a magnet. In fact, I probably should have titled this magnetic domains. It's too late to do that. But what this is showing up here, this is showing the magnets before they're magnetized, a metal before they're magnetized. The arrows are representing the individual magnetic fields inside of there. When you apply a magnetic field to this material, to the metal, it can temporarily realign those. So now this piece of metal, iron, nickel, or cobalt, they're magnetic domains, their electrons all get spinning the same way, and it'll be magnetic. If you were to have a piece of molten metal and you applied an electric current to each side of it and let it cool, you would end up with a magnet. You can also get a piece of metal and you can force these domains into order by applying an extremely high amount of voltage and current. And in fact, I've got plans for a magnetizer we'll make. It's kind of dangerous, but it's kind of cool. But it's kind of neat because you can take anything like, I know when we made them, we stuck scissors in them and we magnetized them. And so what happens here, this illustration is showing that when you put a piece of metal near a magnetic field, it'll turn this one temporarily into a magnet if it's iron, nickel, or cobalt. There's the magnetic lines of force down there. That's not the greatest, it's not coming out the greatest on my picture here. So we've got the north and the south end of a magnet, and the magnetic field lines come out the one end and they come back over here. The Earth is a giant magnet itself. We've got spinning molten material. We have a magnetic field. And if you put one of these really lame-o bar magnets together on a piece of paper and sprinkle some iron filings, I'm going to have you do this in a moment, you can actually see the magnetic lines of force coming out. And so the idea is that an unmagnetized piece of metal, the domains, those atoms act just like little magnets with north and south ends. When you get it magnetized, either by putting high current through it or getting it near a magnet, they'll get aligned. And now all of these go in the same direction. You get a magnetic force. And I'm going to pause. I'm not going to pause here. I'm going to do this one here. Last part of this, electric motor, because that leads into our activity. An electric motor are coils of spinning wire surrounded by magnets. So you got coils of wire. Usually, a lot of times they'll make the coil of wire spin. They might, depending upon the design, they might make the magnet spin around a coil. But when you get coils of copper wire spinning around a magnet, and something kind of like this diagram is showing, you're going to cause electric current. And that's how our power plants work. Whether it's a nuclear power plant heating up water, you having steam make one of these spin around, or we have a hydroelectric power plant where you got water flowing down, turning a turbine, moving these electric coils through the magnetic field. That's how we generate electricity. And we're going to be messing with that now. So at this point, I think the notes part is done. I'm going to have you mess with the magnetic lines of force and then with the bar magnets a little bit, and then we'll have you get working on your challenge. So with that, I don't think I have anything else. Oh yeah, it's time to do it. Bar magnet and iron dust. Can I turn this off now? Are you finished? Did you have enough time to write all that complicated stuff down? All right, goodbye everybody.